Well, welcome back, everyone, and thanks for coming. Last time we were talking about cross-sectional studies, and I used the following example, looking at the relationship between smoking and existing coronary heart disease, prevalence of coronary heart disease at the 1956 exam using people from your Framingham data set. And we found in that data set that the prevalence of coronary heart disease was actually lower, 4%. Than among the smokers than it was among the non-smokers, where it was 5%. We calculated a prevalence ratio, and we observed a value of 0.82, saying the prevalence of heart disease among the smokers is only 82% of that among the non-smokers. And we talked about possible explanations, reason for that association, because it was prevalence data. Prevalence is a function of incidence, prevalence is a function of duration, and I also mentioned in cross-sectional studies there's always the potential of what came first. In the case is what's influencing what here? Smoking influencing heart disease or heart disease influencing smoking. And that was probably the case in this study. And those are limitations of cross-sectional studies. There are multiple explanations for finding an association, and it might not be easy to determine which one is the most likely explanation for any one study. I also mentioned there are other possible reasons for an association in any type of study, including cross-sectional studies, and one of them is bias. Now let's talk about what bias means, and I'll talk about bias continually during the next few weeks of this course when I talk about the other study designs. First of all, what is bias? Bias is an error, a mistake in the design of a study. Remember, we talked about study designs. What do they involve? In a very big picture, they involve enrolling people in a study, collecting information, data on those people, and doing some analyses. So there are two potential sources for bias creeping into your study, two potential mistakes. You could make an error in who you enroll in a study. You could enroll the wrong people in your study. So just from the get-go, from the first step, you've got the wrong people in your study, you're going to get the wrong answer from those wrong people. That's a potential type of bias. The other type of bias is collecting the wrong information. Maybe you're making mistakes when you collect information in a study. That's errors in data collection, measurement. And that means from the get-go, again, you're going to get a wrong answer, a wrong conclusion from your study because you're collecting incorrect information on people. So what a bias means is you're going to result in an incorrect value for your measure of association, your risk ratio, your odds ratio, or in the example we're looking at, the prevalence ratio. So I'd like to use that data to potentially describe two potential types of biases. One due to enrolling subjects incorrectly or in error, one collecting wrong information people in error. That could explain why we're seeing this somewhat unusual result in our cross-sectional study, that the prevalence of heart disease is actually lower among the smokers than it is among the non-smokers. The prevalence ratio is 0.82. So in general, there are two types of bias. Bias due to enrollment, let's call those selection bias, and bias due to the collection of data, measuring things on people. Let's call that measurement bias. And both of them could be true in this cross-sectional study we just looked at. So for example, let's look at selection bias. Well, in the very first week of this course, I gave you a lecture about the history of epidemiology, and talked about some of the key figures in the past that help develop the methods that we use in epidemiology, and talked about one key study, the Framingham Heart Study, as maybe the most famous example, well-known example of a cohort study. Cohort studies are something we'll talk more about in a couple of weeks, and I'll talk more about the Framingham study at that time in detail, but we've been using the Framingham data set, at least a teaching data set that was furnished by the National Heart, Lung, and Blood Institute from NIH. But I will tell you in a couple of weeks, and I mentioned this in the very beginning of the course, that originally there were 5,209 participants in the Framingham Heart Study when it was developed around 1950. We're using a subset of that data. We're using a data from people who were attending the 1956 exam. We only have 4,434 people in our Framingham data set. And one thing we might want to be concerned about is who are the people we're missing? Who are the people who were in the original beginning of the Framingham Heart Study, the 5,209, and are not in our data set? We are missing 5,209 minus 4,434. We're missing 775 people. Why are we missing them? Well, some of those people might have unfortunately died between 1950 and 1956. They weren't alive. They weren't able to come, obviously, to the 1956 exam. Other people might have moved out of Framingham or for some reason or another decided not to come to the 1956 follow-up examination. We're missing those people. And the other thing we not have a clear idea for is how the National Heart, Lung, and Blood Institute created this teaching data set. Maybe by design they eliminated some of the people to give you a slightly different data set than what was in the original and in the true Framingham data set, because we mentioned at the very beginning of this course, these data are at our disposal for teaching purposes, but not for writing research papers. So maybe the National Heart, Lung, and Blood Institute, NIH, has removed certain people from the Framingham data set to create the teaching data set that we have. One way or the other, we're missing 775 members of the original Framingham cohort. And that could be the reason for a selection bias. Maybe the people we're missing are mostly smokers, or maybe they're mostly non-smokers. And in addition, maybe they're people who did or did not have previous coronary heart disease, meaning the reason that people are missing might be related to the two factors we are relating to each other in our cross-sectional study, namely smoking and existing coronary heart disease. And as a result, we might be getting an incorrect picture of the association between smoking and existing heart disease that we would have seen if we had all 5,209 people. So, for example, let's suppose, for example, that what we are missing among the 775 people are lots of people who were smokers who really had coronary heart disease. We're also missing lots of people who were non-smokers and did not have coronary heart disease. So let's imagine that if I included those other 775 people, instead of seeing 86 people in the cell corresponding to smokers who had heart disease, we'd see a bigger number. A bigger number in this group of people who smoke and have coronary heart disease means that the prevalence I'm reporting among the 4,434 people is an underestimate of the prevalence I would report if I had those extra people who were smokers and had coronary heart disease. On the same idea, let's suppose among the 775 people there were lots of people who were non-smokers who did not have coronary heart disease. So that number, 2,145, would also get bigger if I had all 775 people who were initially in the Framingham cohort. That means if I calculate the prevalence among the non-smokers, it's going to get smaller. So maybe the reason that I'm seeing a smaller prevalence of coronary heart disease among the smokers compared to the non-smokers is due to the selection bias. The people who I have not selected for my study, the 775 people who were originally enrolled in the Framingham cohort, tended to be people who either were smokers with heart disease or non-smokers without heart disease, and the result has led me to a table that we've been analyzing based on eliminating those 775 people and giving me a prevalence ratio that was in error, smaller than it should be, because of that selection bias. So selection bias is a potential reason for finding a result in this cross-sectional study, and it also has to be considered as potential problems in any type of study design that we will be looking at. So that's one type of bias due to who we are enrolling in our study. But remember, I said a study design involves a couple of things. It involves enrolling people and then collecting data on those people, measuring things on people. And that's where the second potential bias could come into play in this cross-sectional study. It's a measurement bias. Suppose the smokers see their doctors less often because they're smokers and not health conscious. They know smoking is not good for them. They're saying, heck with it, I'm not going to bother seeing my physician every year like I'm supposed to do. And therefore, they are worked up less rigorously than non-smokers. Therefore, when you ask the question at the 1956 exam, have you ever been diagnosed with coronary heart disease? They might say no to that question, which is a true answer. They have not been diagnosed, and maybe because they were never tested. So it's possible that we might be underreporting all the cases of heart disease among the smokers. Meaning when I looked at this cross-sectional study among the 2,181 smokers, when they were asked, have you been previously diagnosed with coronary heart disease, 86 of them said yes, and 2,095 said no. But if some of those people who said no really did have coronary heart disease, but just had never had it diagnosed, they would have been moved into the yes group if they had been tested, as often say as the non-smokers had been tested. So maybe that underreporting of true cases of heart disease among the smokers is the reason we're seeing the smaller prevalence among the smokers, and the reason we're seeing a prevalence ratio showing that smokers have less heart disease than non-smokers. So a measurement bias is another potential reason for finding this association in this cross-sectional study, as it is for many types of studies that we'll be talking about in future weeks. So those are the two types of bias, selection bias and measurement bias. Often measurement bias is broken into two general categories, reflecting the reasons for misclassifying, mismeasuring information on people. In one situation, we refer to the error as reflecting random misclassification, meaning in the example we've been looking at, let's suppose that both the smokers and the non-smokers have some misclassification. In both groups of people, there are some people who are saying no, they've never been diagnosed with heart disease. And it's because they were never tested. And if they had been tested, they would have been answering yes, because the diagnosis of heart disease may have been determined at that test. So if you're making errors which are the same amount in both the two groups you're comparing, the smokers and the non-smokers, that's what we mean by random misclassification. The misclassification of coronary heart disease is the same among the smokers and among the non-smokers. The chances of making an error is the same in both groups. It's unrelated to smoking status. When you have that type of misclassification of the random type, the usual implication of that is when you measure an association in your data set, you measure something and you see the value you obtain is often an underestimate of the true value that you'd like to be seeing. And to drive that home in the most extreme case is, let's suppose I was making mistakes in measuring outcomes on people. And what I basically was doing was just measuring noise among people. I was just flipping a coin. If the coin came up heads, I was calling that person as having a case of coronary heart disease. If the coin came up tails, I said that person does not have coronary heart disease. I'm making lots of errors in both of my groups, my smokers and my non-smokers. And in some sense, I'm making the most extreme types of errors. And if I did that study, I'd find no association whatsoever in the reported coronary heart disease status based on those coin flips, and whether a person was a smoker or a non-smoker. So when you have random misclassification, the usual implication is that you have a bias towards the null value. Underestimate the true association between the two factors you're considering. And that's true whether we have a cross-sectional study, as in this case, or cohort studies, case control studies, or experimental studies, as we'll talk about in future lectures. The other type of measurement error is much more serious, the non-random type. That's where the mistakes are dominant in only one of the two groups you're comparing. Say it's the smokers only who are making errors in reporting whether they really do or do not have coronary heart disease. In that case, the measure of association we see could be an underestimate, it could be an overestimate, depending on the amount of errors occurring in the smokers or the non-smokers. So if you feel you have non-random misclassification, then you have a problem. You don't know whether your observed measure of association, prevalence ratio 0.82, is underestimating or overestimating the true association between smoking and heart disease. So bias is a problem in any type of study. What do you do about bias? How do you address this problem? Well, the first thing is to design studies where the potential for bias is minimal. And Framingham tried to do that. Framingham tried to, in some sense, select random families from the town of Framingham, Massachusetts, when they selected their 5,209 individuals, trying to argue it was a random representative picture of the entire town of Framingham, Massachusetts, not likely to enroll people who are more likely to be in the study if they smoked and have coronary heart disease, minimizing the potential for a selection bias. For measurement bias, yes, they asked people, since the last time we saw you, have you been diagnosed with heart disease? But that's not the only way they made their decision whether the person did or did not have coronary heart disease. Every 2 years, including 1956, when you came back for your biannual test evaluation, you were tested to see if you had any symptoms, signs, evidence of coronary heart disease that you might not have been aware of. And if those tests were positive, that information would be conveyed to your primary care physicians for further workup. So Framingham tried to minimize the potential for both selection and measurement bias. But in general, if you have a bias a potential bias in the study, how do you go about addressing that potential? The first thing you have to do is try to identify the source of the bias. Is it a selection bias? Is it a measurement bias? If so, why is it a selection bias? Why is it a measurement bias? The next thing you'd like to do is to decide, is this a serious problem or a minor problem? Is it going to give you an answer that's a little bit biased or greatly biased? So you try to get some idea of the impact, the magnitude of the bias. How far away from truth is your observed measure of association? And more importantly, what you try to identify is the direction of the bias in your study. Is your result that you observe, your prevalence ratio of 0.82, an underestimate or an overestimate of the true association between smoking and the prevalence of heart disease? The problem is, unlike the next topic I'm going to be talking about, confounding, for biases there's very often little you can do in the analysis of your data set to correct for that bias that happened when you were designing your study. So the best way to handle or minimize bias in epidemiologic studies is to design studies where the potential for bias, selection bias or measurement bias, is minimal. Well, we'll be talking more about bias in future weeks when we talk about other study designs. What I'd like to talk about next is another general reason for finding an association between two factors in a study. I'd like to introduce the concept of confounding. So I'll see you next time.